Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the whole of the unit of quantitative chemistry. Now this video does start off going through combined and triple, and at the end of the video I'll just go through some triple only content. So even if you're doing combined science, this video is for you as well. But you don't have to watch the whole thing. I will say when we start the triple content only. This topic starts off by looking at something called the conservation of mass. And here I've just got a simple reaction. I've got magnesium and oxygen making magnesium oxide. And here what I've got is I've got a crucible on top of my Bunsen burner. If I put a lid on top, it actually makes it a little bit better, so none of the magnesium oxide can escape. Now, although I have the word equation up here, what I'm going to show first to you is how to turn this into a balanced symbol equation. So I've got magnesium and oxygen reacting to make magnesium oxide. So first up, I write out what I have. So magnesium in the periodic table is Mg, and I'm reacting it with oxygen. Now, what you've got to remember is oxygen is diatomic, meaning it travels around in a pair. And this reacts together to make magnesium oxide. Now, magnesium oxide has the formula MgO. The reason why it's MgO and not MgO2 is because of the fact magnesium makes a 2 plus ion and oxygen makes a 2 minus ion. When they bond together, they are in a 1-to-1 ratio, so you only need one of each. The next thing I do in a balanced symbol equation is I put my state symbols in. Now, magnesium is a metal and it's found in the solid form, so I put an S in brackets. Oxygen is a gas, so it's represented with a little g, and it's making magnesium oxide, which will be formed in my crucible, which is a solid as well. Now, currently, this isn't a balanced equation, and there's a way that you can balance equations dead easily. What you can do is you can put a line down the center of your equation, and you count up everything you have on both sides of the equation. So I have on both sides magnesium and oxygen atoms. On this side of my equation, I have one magnesium, and I have 2 oxygen atoms. And on this side of the equation, I only have 1 magnesium and 1 oxygen. If there is no number before it, just always assume that it's just 1. Now, it would be dead easy to balance this if I could just put a little 2 at the end after my MgO, but I can't do this because this would change the chemical that it actually is. It would make it magnesium dioxide, which doesn't work. So what you need to do is you need to change numbers at the front. So let's balance up my oxygens. If I put a 2 here, now I end up having 2 magnesiums and I have 2 oxygen atoms. And then on this side of my equation, to finally finish it off, because now I've got more magnesiums on this side of my equation, all I need to do is put a 2 in front of the magnesium here, and that is a balanced equation. Now, this reaction is really good for investigating the conservation of mass, because what you can do before the practical is you can weigh out how much magnesium you have going in. So for example, if I weigh out 5 grams of magnesium and I'm reacting it with my oxygen, and I could then at the end of my practical I could weigh out my magnesium oxide and I could work out how much oxygen has reacted with it. Say for example, if this is 7.5 grams, I could work out that it's reacted with 2.5 grams of oxygen. Now, a bit later on in the video, we are going to look at how you can predict how much magnesium oxide you would get from starting with magnesium. But to start off the video, we will just leave it like this to show you that this is showing the conservation of mass. The next thing we are going to talk about is relative atomic masses and relative formula masses. And this is where you need to start being good at using your periodic table, because we are going to look at how to find the relative atomic mass of an atom. So for example, if you were told to give the relative atomic mass of magnesium, what you need to do is go to the periodic table, and you will notice there is two numbers by magnesium. There is 12, which is the atomic number, and 24, which is called the relative atomic mass. So it's always the top number, which is the relative atomic mass. Sometimes given the name RAM. And if we look at chlorine as well, chlorine has atomic number of 17, and it has a relative atomic mass of 35.5. Now, what is the importance of this relative atomic mass number? Well, it tells you how many grams are needed for 1 mole. So if I was looking at magnesium, it would be 24 grams in 1 mole. Now, this means if I had 24 grams, I would have 1 mole of it. And if I had 48, I would have 2 moles of magnesium. So let's take it a bit of a step further, because atoms are usually found bonded to something else in compounds. So let's have a look at this compound down here, which is magnesium chloride. How would I get its relative formula mass? Well, what you do is you add up the relative atomic masses of all the atoms that are present inside there. So I've got 1 atom of magnesium and I've got 2 atoms of chlorine. So I'm going to do 24 plus 35.5 plus 35.5 again, and this will give me the relative formula mass of magnesium chloride. And this gives me an answer of 95. So this means I would need 95 grams of magnesium chloride to have 1 mole of it. Let's go a bit more in depth and have a look at what moles actually are now and why it's important. Now, what you can do with these relative formula masses is you can work out the percentage by mass of a particular compound. So if I just look at lithium carbonate, for example, I can work out how much of lithium carbonate is lithium by doing the relative atomic mass of lithium in here and dividing it by the relative formula mass of the whole compound. So let me just show you what I mean by that. So the amount of lithium in lithium, there's 2 atoms of lithium in a compound of lithium carbonate. So I'm going to do 2, and if I look in the periodic table, lithium has a relative atomic mass of 7, and I'm going to divide it by, if I do carbon as well and oxygen, just write them out, the numbers that you see in the periodic table. Well, I'm going to do this 2 times 7 because there is still going to be lithium in the whole compound, and I'm going to add it to carbon, which is 12, and I'm going to add it to oxygen, and there's 3 of them, so it's going to be 16 times by 3. And if I times it by 100 to put it in a percent, and that will tell me that 19% of my whole compound is lithium. The reason why we use this term mole is because atoms are incredibly small. So we came up with a number of atoms that would represent 1 mole, and that number is 6.022 times 10 to the 23 atoms. This is how many atoms there are present in 1 mole, and it's sometimes called Avogadro's constant. So how do you work out how many moles of a substance you have? Well, what you need to do to work out the number of moles is moles equals the mass divided by the relative formula mass. And I've put it into a calculation triangle here because sometimes you need to rearrange it. For example, if you were trying to work out mass, that would equal moles times by the RFM. And the RFM would equal the mass over moles. And the one that we're looking for, the moles, equals the mass divided by the RFM. So let's stick with magnesium chloride because we looked at it a second ago and we worked out that the relative formula mass of magnesium chloride is 95 grams per mole. So what happens if I want to work out how many moles are present in, say, for example, 10 grams? What I would need to do is I would do the moles equals the mass, which is 10 grams, divided by the RFM, which is 95 grams per mole. And that gives me an answer of 0.105. And moles doesn't really have a unit, but you can write mole at the end of it and the examiner would know what you were on about. I like to always put in grams per mole as well for relative formula mass because it helps me understand it. Now, as well as using the mole to work out the number of atoms you have, you can also use the mole to balance equations. So here I've got a question asking me to balance the equation for the burning of methanol here, and the way to do it is by working out the moles that you have of each of your substances. So let's do that then. I'm going to work out first the number of moles of methanol I have, which is my CH3OH. And the way to do that is do my mass, which is 64 grams, divided by the RFM. So I've got one carbon, and carbon has a relative atomic mass of 12, plus there's 3 hydrogens, then 1 oxygen, which is 16, and then another hydrogen, which is 1. And when you do that calculation, you find out the answer is 2. Then I also have oxygen, and oxygen has the molecular formula O2, and we've got 96 grams of oxygen, and oxygen has a relative atomic mass of 16, and there's 2 of them, 16 plus 16. So it's going to be 96 divided by 32, and off the top of my head, that equals 3. And then we have carbon dioxide, which is CO2, and CO2 has 88 grams. And I know the relative formula mass of carbon dioxide is 44. And that gives me an answer of 2. And then finally, I have 72 grams of water. So 72 grams over water's RFM. There's 2 hydrogens, 1 oxygen, 16 plus 2, which is 18. And 72 divided by 18 is 4. So now I'm in a position to do my balanced symbol equation. So I'm going to write 2CH3OH plus 3O2, then an arrow. It's going to 2CO2 plus 4H2O. As well as balancing equations, I can also use moles to work out what's called theoretical yields from equations. So here it says what mass of carbon dioxide will be made from burning 3 grams of methane in excess air. Now, because we know that oxygen is in excess, it means that my theoretical mass of carbon dioxide being made will be controlled by the amount of methane that there is there. So methane is what we call a limiting reagent in this practical, because that's going to control how much product I'm going to be making. And the first thing to do when you get a question where you're working out a theoretical yield is look at the equation and think, is it balanced? So let's have a look at this one, and I can see I've got one carbon on this side and one on this side, so I'm happy there, but I have 4 hydrogens on this side and only 2 on my product side. So we need to sort that out, and I can do that by putting a 2 in front of my H2O, and then now all I need to do is put a 2 in front of my O2, and that is a balanced equation. The thing to do is work out how many moles of my limiting reagent I have. So let's have a look at my methane, my CH4, and it says that I've got 3 grams of it. So I'm going to work out my moles of methane then, and that will equal 3 grams divided by the RFM of methane, which carbon has a relative atomic mass of 12, and every hydrogen has a relative atomic mass of 1. So it's going to be 12 plus 4, which is 16 grams per mole. And when I do that, I find out that I have 0.1875 moles. The next thing to do is check out the ratio of my limiting reagent to the desired product, which here is carbon dioxide. That's what I'm going to be wanting to work out. Now, this is really important from the balanced symbol equation now, the ratios of them. So for example, if I have 1 mole of methane, I'm going to need 2 moles of oxygen to react with it. And if I have 1 mole of methane, and I react it with these 2 moles of oxygen, I will make 1 mole of carbon dioxide and 2 moles of water. So because in this equation I have 0.1875 moles of methane, I will also have 0.1875 moles of carbon dioxide. The next thing to do is work out the mass of carbon dioxide that you will have, and the way to do mass is by doing the moles times by the RFM. So the moles is 0.1875, and the RFM of carbon dioxide is 44 grams per mole. And when you do this on your calculator, you get an answer of 8.25 grams. You could also work out the mass of water that you want to make as well. And this would really show that ratio idea that I was talking about. You would make 2 times 2 of the moles of water, so 0.1875 times by 2, which gives me an answer of 0.375. So you could work out the mass of H2O by doing 0.375 times by the RFM of water, which is 16 plus 2, which is 18. And that would give me an answer of 6.75 grams. Now, I said I'd return to that magnesium and oxygen reaction that happens in a crucible a bit later on, and that's what I'm going to do now, because I'm going to look at this reaction and I'm going to work out the theoretical yield, and then I'm going to look at the actual yield and work out the percentage yield for my reaction. So here I start off with 3.2 grams of magnesium, and I'll just say that in reality I made 6 grams of magnesium oxide. Oh, I need a little 2 there just to balance it up. And what I'm going to do first is work out the moles of magnesium I start with, which will equal 3.2 grams divided by the relative atomic mass, which is 24 grams per mole, and that gives me an answer of 0.13 recurring. Now, because I know my moles of magnesium, I'll have the same moles of magnesium oxide because they're in a 1-to-1 ratio. So I'm going to make the same amount of moles of magnesium oxide, which will be 0.13. Now, what I need to do now is I need to work out my mass, my theoretical mass of magnesium oxide, which will equal 0.13 times by the relative formula mass of magnesium oxide, which we know is 40 grams per mole, because magnesium's is 24 relative atomic mass and oxygen's is 16. And that gives me an answer of 5.3 grams. Now this is my theoretical mass, this is the maximum mass I can make. So you can see up here, I chose 6 grams at the start, that was a bad idea, let's scrub that off. Imagine we actually get 4 grams of magnesium oxide. Now I can work out my percentage yield by doing the actual yield, which we got to be 4 grams, divided by my theoretical yield, which is 5.3 grams, and then timesing it by 100 to put it into a percent. And that gives me an answer of 81.1%. Now the reason why I had to change this from 6 to 4 is because of the fact you can never get a percentage yield over 100%. You're always going to get a value lower than that, and there's some reasons why this could happen. You could have some unreacted magnesium still in there. You could also not have left it long enough for the reaction to have gone to completion, and you can also get transfer losses. Now, it's quite easy, isn't it, to work out the number of moles of a solid that you've got. But what would I do to work out the number of moles that I have in a liquid? Well, what you can do is you can do moles equals the concentration of that liquid times by the volume. And that's because concentrations are usually supplied in moles per decimeter cubed. For example, you might see on a bottle of hydrochloric acid, it might say that this is 2 moles per decimeter cubed hydrochloric acid. Now, to work out the number of moles that you have, you need to know the volume that you have. So if I have 25 centimeters cubed of 2 moles per decimeter cubed HCl, you could work out the number of moles in there by doing the concentration, which is 2 moles per decimeters cubed, times by the volume. Now you're going to have to put the volume into decimeters, and the way to do that is by dividing by 1,000. So it's going to be 25 centimeters cubed over 1,000 centimeters cubed, because that'll put it into decimeters, and that will tell me the number of moles that I have, which is 0.05 moles. It's just really important to remember to always, if you've got it in centimeters cubed and you have the concentration in moles per decimeters cubed, always turn it into decimeters first. Remember that there are 1,000 centimeter cubed in 1 decimeters cubed. You may also see the concentration written as 2 and then a capital M, so just watch out for this in an exam as well. If you are doing combined science, well done, you have reached the end of the video. If you are doing triple science, don't worry, you've just got a little bit more to go, not too much. What we're going to do now is talk about atom economy. I know we've talked about percentage yield a little bit, but this is a little bit different. What you need to do to calculate the atom economy of a reaction is you've got to think about how much of the useful product is made out of all of the products. So if I have a look here, this is how I smelt iron. in order to get iron on its own. And here is the word equation for this smelting. I have 2 moles of iron oxide reacting with 3 moles of carbon, and it's making 4 moles of iron plus 3 moles of carbon dioxide. So in this reaction, you are wanting to collect iron, and you are also collecting some waste carbon dioxide. So the way to do this is the MR of my desired product. The relative atomic mass of iron is 56 grams per mole, and in total I have a ratio where I have 4 moles of iron, so I'm going to have to times it by 4, so it's going to be 56 times by 4 on the top of my equation, and over the MR of all my products, well, I've got 56 times by 4 because it's still one of my products, and I'm going to add it to the relative formula mass of carbon dioxide, and remember there's 3 of them, and carbon dioxide has a relative formula mass of 44 grams per mole, so it will be 3 times by 44, and then I'm going to times my answer by 100 to put it in a percent. And that gives me an answer of 62.9%. I can also work out the number of moles that I have in a gas, because 1 mole of gas always occupies the same space, which is 24,000 centimeters cubed, which is the same as writing 24 decimeters cubed. So the way to work out the number of moles is by doing moles equals the volume of gas that you have divided by 24 decimeters cubed. So let's look at a quick question. You could work out how much space would 10 grams of O2, and I'll put the little gas sign, take up. Well, first we'd work out the number of moles of oxygen we have, which would equal moles equals the mass, which is 10 grams, divided by the relative formula mass of oxygen, which is 16 times by 2, which is 32 grams per mole, which gives me an answer of 0.3125. And then to work out the volume, we could do the moles, which is 0.3125, times by 24 decimeters cubed, and that will give me the volume in decimeters cubed. And the answer for that is 7.5. The last thing we're going to go over is titrations, and that's going to have a lot to do with the equation that we looked at earlier with concentration. So I'm just going to put that triangle just down here so we can refer to it, which is concentration times by volume, and we've got moles on top. So how do I do a titration, and what should I see? Well, there's a few pieces of equipment we need to know first, which is a burette. We have our conical flask down here, and what you have in your conical flask is an unknown concentration of either acid or base. So the first thing you need to do in your titration is add 25 centimeters cubed, or it could be 50 centimeters cubed of unknown concentration. For the purpose of this, we are going to put our base in our conical flask, because that's going to be our unknown for this. So we're going to add 25 centimeters cubed of unknown concentration base to the conical flask. And why we're doing this whole titration is basically to try and work out the concentration of this unknown. So what we're going to do that is we're going to carry out a neutralization reaction. When I added enough acid to it, we will have a completely neutral solution, and I can work out the concentration of this base from that. And the way I'm going to add my 25 centimeters cubed accurately is using a pipette. The next step is I'm going to add an indicator to my base. Now, for the purpose of this, I'm going to use the indicator phenolphthalein. So add 2 drops of indicator, which will go pink / purple. We're going to use phenolphthalein. Now you can use your own indicator if you know a different one, but I always use the same one. I always remember phenolphthalein, it goes pink in basic, and when it's in acidic it is colourless. Then what you're going to do is add the known concentration of acid dropwise from your burette. And you're going to keep doing this until you get the colour change. You're going to stop adding when colour change. And you keep doing this until you get what's called concordant results, which basically means that they're only a small fraction away from each other. And at the end, what you do is you get a mean titer from this, and then we can use this and a titration calculation to work it out. So what we're going to do now is have a look at a titration calculation. So we know how to carry out one of these calculations. So here we've got one. It says in a titration, 25 centimeters cubed of 0.2 mole per decimeter cubed sodium hydroxide solution is exactly neutralized by 22.6 centimeters cubed of a dilute solution of hydrochloric acid. Calculate the concentration of the hydrochloric acid. So what I need to do is I need to first, I like to always separate out into acid and into base, and I always write NCV on both sides, NCV, and then I start writing out what I know already. Now here I've got 0.2 moles per decimeter cubed of my base, so this is the known concentration, and what I'm going to finally get to is my unknown concentration of hydrochloric acid. So let's whack that in, 0.2 moles per decimeters cubed. And my volume of it is 25 centimeters cubed, which can also be written as 0.025 decimeters cubed. The reason why I'm putting it into decimeters is because if you remember, to get the number of moles, what you do is you do the concentration times by the volume, and the concentration is being given in moles per decimeters cubed. Now I can also put in the volume of acid because that has been given in the question, so let's do that. I have 22.6 centimeters cubed, which can be written in decimeters as well, 0.0226. Now, what I'm going to do next is work out the number of moles of my base, which I can do by doing the concentration times by the volume. So that's going to be 0.2 times by 0.025, which gives me an answer of 0.005 moles. Now, because I have 0.05 moles of base, I can use my balanced symbol equation to work out the number of moles of acid it must have reacted with. Because they're in a 1-to-1 ratio, basically meaning if I have 1 mole of base, I have reacted it with 1 mole of acid to completely neutralize it, I will also have 0.005 moles of acid. And then finally, the last thing to do is do the concentration, do the number of moles divided by the volume, and that will give me the concentration. So I'm going to do this 0.005 divided by 0.0226, and remember that's in decimeters cubed. I can now put that on my calculator, and I've got a concentration, which is 0.19 moles per decimeters cubed. This is my final answer. I'm going to underline my answer and I'm going to circle my units just to show the examiner that I've finally worked it out, and this is my final answer. Now, I hope you have enjoyed today's video. Remember, if you have, please drop it a like and subscribe to the channel.